Okay, we're off, recording again. So today for the third lecture of this week, I'm going to finish off the rendering material, actually talking about some fairly technical stuff about what's happening behind the scenes when you're rendering stuff. Might find it a little bit challenging. And then we'll go into the tutorial where we'll look at both last week's homework and forward to this week's. But let's start with the lecture part. Okay, so it's rendering part 2. So just as a basic recap of what we covered on Monday, we're looking at how you generate images on TVs and nowadays monitors, and we've discovered that it's all an illusion. Illusion in a couple of ways. Some of it's the illusion of motion, where you have the static pictures and your eye fills in the blanks, and then we have the perceptual illusions about how colour is simulated and tricks your primitive human eye. There we go. As Morpheus might explain, what if I told you that moving pictures aren't really moving? What if I told you that that isn't yellow? Has anyone seen the new Matrix site that just went up yesterday? No, it's not bad. It's a teaser for the new movie. And the interesting thing is, if you go and look at it, be very conscious of what time it is when you're looking at it. That's all I'll say. I have mixed feelings about the Matrix movies. Even the first one's not really that great, but never mind. It was okay in its day, almost. Yeah. Okay. So, on Monday I was largely talking about the way old-fashioned cathode ray tube displays worked, because they are the basis that everything was actually built around. But as you'll know, nowadays we actually use liquid crystal displays or other kind of technologies. And they're a bit different. It turns out they can update at far faster speeds than old TVs, so you can get higher frame rates out of them. They're also thinner and lighter, which is convenient. So nowadays, a common thing might be to have 60 frames per second, or 60 lies per second, as I call it there. The reason I call it lies is there's an old quote about cinema, which is cinema is 24 lies per second. But nowadays it's more than that. And you can get these even higher refresh rates if you want. But the interesting thing is, even though it's different technology, in a lot of ways they're just emulating CRTs, and that goes right back to emulating things like the way they scan the image out, top to bottom, left to right, which is not really technically necessary as such, but, well, you have to do it in some order, so they just preserve the order that was established by old television technology. That actually has some consequences. It means that LCD-based displays are subject to some of the same technical problems and artifacts that we used to have with TVs. And one of those is that remember I've talked about the frame buffer, which is just this array of pixels, that's what's going to be on your picture when you see it. Well, bear in mind that image is being kind of drawn to your display device kind of progressively, so it's kind of coming down like this, fairly quickly, but it's still doing it. Now the thing is, if that's happening, and you're still updating the frame buffer, like you're still drawing stuff in your game, you could get weird effects could occur, such as you might find that the scanning beam runs past part of your image before you've actually drawn the thing that should be there. Or maybe it catches you between erasing one thing and drawing the other. Because sometimes when you update a screen, there are a couple of ways to do it. One is you clear the screen and start from scratch every time. The other is you take the previous image and maybe you modify it. You take this bit away and you put this bit back. But the problem is, all that stuff's kind of going on, and if the scan happens to catch you in the middle of these updates where the picture hasn't been fully drawn to completion yet, you're going to see some weird stuff. Partial images, as I call them. So this can manifest in a couple of ways. One is flickering objects, which is something you used to see a bit on kind of 2D games. What would maybe happen is that as the game was trying to build up an image, it was drawing some little guys on the screen, or sprites as they would be called, but it hadn't quite done it yet, so the scanning beam comes past and that sprite wasn't there yet, and then on the next frame it is there, so it kind of goes away and comes back and you see like a flicker that looks a little bit ugly. And there's the other one which you see more commonly on modern games, which is screen tearing. That's an artifact that I think you might have seen, where what's happening is the scanning beam has kind of caught you between two frames. You're partly computing frame n and you're partly computing frame n+1, and the beam comes down and you haven't quite finished, so you end up getting a nasty mixture of the two. So firstly, I'll show you what flicker looks like. So very famously, the Atari 2600 version of Pac-Man was quite kind of ropey and very prone to flicker. The arcade machine of Pac-Man was very good because it was designed, to be just exactly what it was. But when they tried to squeeze a full arcade machine, which was worth thousands of dollars or something, into a tiny little home video console that was very primitive and was basically just designed for playing Pong, but they tried to sort of squeeze Pac-Man onto it, there were compromises had to be made. And one of those compromises is the Atari 2600 could basically only draw two things at a time. It could only have two sprites on one line of the screen. So it was basically your guy and the other guy, which goes back to it being essentially designed for doing Pong. So your guy and the other guy. If you had a game like Pac-Man, where you've got your guy and four other guys, it can't actually do that. So the technique that it would use is that it would cycle through the ghosts one at a time. So basically, any given time, it was drawing you and one of the ghosts on that frame. And on the next frame, it would draw you and one of the other ghosts, and then you and the third ghost, and so on. So that meant that each ghost was only being drawn on a quarter of the frames, and the rest of the time it's not there, which makes it flicker like a flickery thing. This is kind of what it looked like. See, that's there's really only one sprite available for doing the ghosts, and it's having to take turns each doing the four potentially different ghosts that exist. Rather ugly behaviour. Okay. Now, the interesting thing about this is it does sometimes look quite bad. And particularly if you see it on a modern emulator, it might look really bad. I've tried to show you on an actual television set though, because it turns out it didn't look quite so bad in real life. In fact, back when this kind of thing was coming out in the late 70s, early 80s, and people had basically bad televisions, it turns out that one of the things about bad televisions is the phosphors on the screen would have a kind of persistence glow. After you'd struck the phosphor, it would continue to glow for a little bit afterwards, which would mean that when things moved fast on TV, you could kind of see them blurring and stuff. But that had the kind of convenient side effect that for Pac-Man, when it drew that ghost on frame one, the fading phosphor would kind of cover it for the next couple of frames, and it actually wouldn't look quite so hideous as it does on a modern TV. Modern TVs are very sharp, and they don't have image persistence. So the funny thing was, although it's kind of a crummy technique, in reality, if you're watching it on an equally crummy TV, the result was that it would just make the ghost kind of look a bit semi-transparent and kind of spectral and ghost-like. So it actually almost sort of worked. The problem is, the better your TV got, the worse the effect looked. So that was an example of someone almost trying to use flicker for a purpose, with mixed results. Right. And here's the other one that you've maybe seen more recently, screen tearing. Ever seen this in a game? Yeah. So usually it doesn't happen all the time, but you can maybe get yourself into a situation if a lot of things happen, or you maybe move very quickly or something weird happens, you get this horrible thing. So I'll explain what's really going on here in more detail later, but the essential idea is that, this was frame N, which had already been drawn and was on the screen, and here we are trying to draw frame N+1, but we only got part of the way through it when the video circuitry came along and said, tell me what's in memory, I want to put it up on the screen. And because they're not properly in sync, you get this ugly hybrid. Yes, so my point here is that scanning is a tricky business. That's the way the beam scans. Do any of you know the film Scanners, the early David Cronenberg movie? It's not really that related, but Scanners is about people who can read each other's minds by a process called scanning. This is not scientifically accurate, by the way, but the problem is that they have problems with scanning as well, and if two scanners try to read each other's minds, they get into a recursive nested loop where they're each one is echoing their own brain, and their heads explode. It's pretty good, it's a cool film. Right. So this is a bad thing. When scanning goes wrong, it produces unpleasantness. But there are things you can do to limit the damage, and that's mostly what I'm talking about today. Right, so there's an old technique called racing the beam, which had to be used in the early days of games. The idea there was we want to avoid this process whereby the scanning beam is not matching what you've got in your frame buffer, and that's what causes the flicker or the tearing, right? Well, one way to get around that is if you actually know what the scanning beam is doing, like you know the timing of it, it's kind of crawling down the screen like this. And if you just make sure that you're drawing your image just 1 or 2 lines ahead of the scanning beam all the time, you just keep in front of it, or you keep slightly behind it, it's kind of the same thing, right? As long as you keep on one side of the scanning beam, either totally in front of it or totally behind it, and you just keep drawing it like that, and it keeps coming down like that, and you're kind of chasing each other, if you keep the distance the same, it'll be okay, because you'll never get that thing where the scanning beam goes past the writing beam, and that's what causes a screen tear, when you get a mismatch. So that's the general idea. So you try to, the trick is you only modify parts of the frame buffer that the beam has already passed by. That way the viewer won't see as you're writing those pixels in, it won't see the changes happening because you've allowed the beam to kind of get beyond you. So that's called racing the beam. And because if you do that, you won't cross the beam, and that way you won't get the partial image problem. So basically what I'm saying is don't cross the streams. Yes, Ghostbusters. Yeah, I'm throwing out a lot of old movie references because that's just the way I am. So here's the bit in the original one. I haven't seen the sequel, and I'm not going to get into that whole thing, or the remake, whatever it is. Yeah, it's a remake. There's a new remake coming this year as well, though, isn't there? Anyway, that doesn't matter. What happens when you cross the streams?
There's something very important I forgot to tell you.
What?
Don't cross the streams.
Why?
It would be bad.
I'm fuzzy on the whole good bad thing. What do you mean bad?
Try to imagine all life as you know it stopping instantaneously and every molecule in your body exploding at the speed of light.
Total protonic reversal. Right, that's bad. Okay. All right, important safety tip. Thanks, Egon. All right, Ray, take the left. Egon, take the right.
So total protonic reversal, possibly the destruction of the universe, or some screen tearing, depending on whether you get lucky or not. So it turns out, again, back in the old days with the Atari 2600, racing the beam was in fact the only technique, because as I mentioned, I think in the first lecture, that machine didn't have a frame buffer because it didn't have enough memory to store one. Remember, that's the one that only had as much RAM as you need to store a tweet, or less. So it actually had to construct the image on the fly, line by line, absolutely in sync with the scanning beam. So when you wrote for that machine, you needed to know what line of the screen the TV was on, and you wrote out the pixels for that line as it was happening. That's why it was hard to program that machine, which is kind of amazing. So this is completely impractical and it's very restrictive. You have to design your whole game around this reality of always being able to know what you're doing, and you don't have many instructions to do it in. They're writing an assembly language and they've only got a couple of dozen instructions to write out each line. The timing is really difficult. There's in fact been a whole book written about this called Racing the Beam, which is a fairly short book and quite a fun read. But if you haven't got time for that, there's an article in Wired magazine that explains a little bit about how that kind of stuff was done. God, no way. So this sort of, please stop annoying me. You might want to look at this once I put the slides up. Some stuff about how Pitfall actually had to work. You might find it instructive, it's not very long. Right, so the way I sometimes think about this is that the scanning beam, which was originally the actual physical electron beam of an old CRT, or nowadays is just the update order of the pixels on your screen. I think of that scanning beam as like, it's scanning across the horizon again and again and again. So it's the Eye of Sauron watching over the landscape of Mordor, and you don't want to be seen by him, because that's when the bad stuff happens. The bad stuff happens when the eye can see you while you're in the middle of drawing the picture, and if you do that, it can look bad. So ways of hiding from the Eye of Sauron. One of them is called VSync. How many of you know about VSync? I think it's an idea people are aware of. How many of you actually understand it, though? How do you really know what VSync is doing? Yeah, maybe not so much. It's like, you know it's there, it's like a driver setting, or you hear it as an option in games. So I'll explain what's actually happening. The trick with VSync is you don't want the Eye of Sauron to see you while you're writing to the screen. One very brute force way of preventing that is don't ever draw the screen while he's looking. And it turns out that when you finish drawing a frame, especially on an old TV, it would draw the frame down to the bottom, and then it had to pull the electron beam right back up to the top, and that took some time. So there's actually a little bit of time at the end of the frame where the beam is basically switched off as it's being pulled back up to the top. And although the modern technology doesn't have that restriction, it doesn't work that way at all, that behaviour has been retained. There is in fact a little extra millisecond at the end of the frame where nothing's happening, where it's in theory waiting for the beam to go back up to the top. Now it turns out if you can write to the screen during that 1 millisecond when Sauron is blind, then he can't catch it, and then when he draws the next frame, it looks good because he hasn't spotted you while you were doing your drawing. So that's the idea there. So there was indeed a delay at the start or end of the frame, and the beam was switched off, and you could draw stuff without it causing artifacts. This period is called the vertical blanking interval. And it still exists in modern standards, like even HDMI, digital interfaces. They've got a vertical blanking period where there's just nothing really happening as a legacy of all this. So here's a picture of kind of how a TV frame is organised or was organised. And the idea is that this is the if you imagine the signal that's being sent over the wire, right? It turns out that the early part of the signal is this empty period called the vertical blank, during which time the electron beam is moving. Then you get down to the part of the signal where the actual meaningful picture information is being scanned, right? That's when that's coming out. And even when you're doing that, when it gets to the end of one row, it also has to kind of come back to start the next row. So there's a little piece of time where the beam was coming back, and that's called the horizontal blank. And that's another period where it's potentially blind, although I think nowadays they can probably eliminate the horizontal blank. But it used to be a time where you could do some tricks during the horizontal blank. But most typically you do your tricks during the vertical blank, or the overscan, which is kind of similar. The overscan is just like the kind of extra bit at the bottom of a frame. In fact, that's in the old days, that's where you could put information like the subtitle information is encoded in the frame in an invisible part of the picture down at the bottom. And if you've got a TV that can decode subtitles, it's fetching the information out of that invisible part of the picture. Kind of. Digital TVs are a bit different, but that's the way it used to be. So that's how the frame is organised. So the VBLANK itself lasts for about a millisecond, and it's a time when, as I say, you can update the screen without being spotted. So here's the trick. The trick is, do all your writing during that magic 1 millisecond, and you won't have any flick, and you won't have any tearing, and that sounds good. And of course, if we talk about a 60 frames per second system, the whole frame time is about 16 milliseconds and a bit. 1 millisecond of which is the VBLANK, and the other 15 milliseconds is the scan. So the idea is that during the other 15 milliseconds, while it's actually scanning the image out, that's when you go and compute your game logic. You go and update all the stuff in the world, and then you wait for the magic 1 millisecond where you blat it all onto the screen. Unfortunately, it turns out that usually drawing stuff is the part that takes all the time. You can't certainly nowadays you can't actually draw a whole image in a millisecond, which is a pity. It just turns out, there are lots of pixels, and there are maybe, there are lots of objects in the game as well, but it just generally works out that drawing stuff takes more time than updating it. So unfortunately, this 15:1 split is not really what you want. It would really restrict how much you could do, because you'd limit yourself to 1 milliseconds worth of drawing stuff, which is not very good. But it's the germ of an idea that has turned into something a bit better. And that idea is double buffering. Anyone know about that? A couple of hands, okay, but not everyone. Fair enough. Then you'll learn something. That's good. That's why you're here. So the trick with double buffering is that instead of drawing directly onto the frame buffer, where you have this possibility of it being scanned halfway through, you draw it to an imaginary screen somewhere else, a separate buffer, often called a back buffer. And this is a bit like, remember I was talking about flick books? An idea with like a when you're doing computer flick books, you're showing them one picture and you're scribbling the next picture down on your pad, and then you quickly show them the new one, and then you scribble a new one. That's what's going on. The back buffer is the pad of paper where you're drawing your next frame. So the idea is that while one image is being shown to the player, you're preparing the next image. And then when you get down to the 1 millisecond part, the VBLANK interval, what you do is you don't draw the picture because you've already drawn it. You just do the swap. And you can do the swap quite quickly. So that's what's actually done nowadays. So this swap is either copying the image from your back buffer onto the front buffer, and that's just a memory copy, which you can sort of do fairly quickly, or you can actually do something even cleverer than that. But imagine at first that it's a copy operation. So the trick is just timing the copy to be in sync with the VBLANK. Now, the cost of this is that you have to allocate that second buffer. So, you've got like the ordinary frame buffer, which is actually quite a big array, megabytes of memory and stuff. I need to have 2 of them now. There was a time when it was like, when memory was scarce, and that was a bit of a problem, but it's long since got to the point where we just admit that if you want your game to look good, you do that. You allocate 2 screens, one of which you're looking at and one of which you're drawing on. So here's kind of how it works. The idea is that your screen, your graphics card is looking at one block of memory somewhere would actually have a picture on it. Meanwhile, you're drawing the next frame over here on the back buffer, and then when it gets to the VBLANK time, you copy this across. And if you can do the copy quickly enough, you can get the whole image on the screen before anybody notices anything weird, and then the beam comes down now and it draws the next frame and it looks good. So that's the copy technique. But there's a better way that you can avoid the cost of the copy by just telling the graphics card that you want it to render the other buffer instead. Instead of actually copying it, you just say, look, please look at that one. And you can do that now. In fact, you've been able to do that for ages. So now during the VBLANK, all you actually have to do is basically switch 2 pointers around. You just do just a pointer swap to tell the graphics card that you want to look at, screen A or screen B or screen A or screen B, and it just bounces between them. So that's more like this. You have the so-called primary surface in the back buffer. The screen has got a pointer that tells it which array it's looking at, and it's looking at the primary one while you're scribbling on the back buffer. Then when you've done it, you say, at the next VBLANK, please swap your pointer across. And it just does the pointer change to there. The graphics system says, okay, I'm going to start writing to this other buffer now. The screen says, I'm going to start looking at this buffer. And you get a very quick, sort of instantaneous flick. And again, it looks good. You don't get an image tear or a flicker. So the way this would kind of work in practice, imagine you've got the view on your monitor shown here, the contents of your front buffer here, and the back buffer here. So you write frame 1 into the front buffer, and that's what the monitor is looking at. So you see the neutral face. Meanwhile, you go and write the angry face into the back buffer. And then, during the so-called VBLANK, where in theory the electron beam is being moved to the top, even though it's not, right? In theory, while that's happening, you do the switch so that you get frame 2 into the right position. And then, when it draws the next frame, it's going to draw frame 2. Meanwhile, you're working on frame 3 over here. You're drawing the sticking its tongue out face, and you get that one ready, and then when it's finished, you swap, and it just keeps going. So, problem solved. This is how we do good-looking, non-horrible animations for games. Well, if only it were so easy. To a large extent, this is what happens in modern games and has been for ages, especially if they're running in full screen, like console games do, or like a Windows game does if you let it. It takes control of the whole screen. If you've got control of the screen, you're allowed to control these video memory pointers, so you can do this switching trick, and that's fine. But if you're in a windowed environment, let's say you're just literally your game's running in a window, or in our case, you're running inside a web browser. You don't have control of the whole screen. Right? You're just one app of many, and you don't have global authority to write to the screen. And even if you did, you'd potentially have other apps that would also be wanting to do it, and you'll be fighting with each other as to who's in charge and who's getting to control the VBLANK. So you can't actually do it that way. On windowing systems, they have to go back to the old idea that the back buffer has to get copied onto the screen. And it's called compositing. So this is where every window has got its own back buffer somewhere. And nowadays, the operating system does this for you. It kind of copies them across to build up a new image. And the operating system tries to control that and flip the images in a way that makes them look stable over time. Okay, so that thing about being in a window is relevant to us, of course, because we're going to be doing, web page stuff. And as I mentioned on Monday, we're using the HTML5 canvas thing. So you might think that now we need to do something in Canvas to tell it about, I don't know, allocating back buffers and doing buffer flips at the end of the frame and all this kind of thing, which you did used to have to do stuff like this. As luck would have it, Canvas has anticipated our needs, and it turns out it does it for you, right? So when you're doing drawing commands on Canvas, what you're actually doing is you're building up a batch of commands that when you say, context.fill, it's actually writing those out to a back buffer. And then it knows when the VBlank's coming and when you finish drawing, and it actually is coordinating all this buffer copying behind the scenes so that it will do the frame animation basically the right way. And when you use it correctly, you shouldn't really see flickering and tearing when you're doing Canvas work, luckily, because it's doing the right thing. So that's nice. But generally speaking, though, if you are working on another system, like if you were programming a games console or you were writing a standalone app, you sometimes have to think about these things. If you're unless you're using an engine that does it all for you or something, if you're doing this yourself, like if you're directly writing DirectX code or something, you have to be aware of this. You have to allocate buffers and set up how they're going to be swapped, and you have to know what you're doing. Right. So double buffering is a nice technique, and it mostly works quite well, except when it doesn't. One of the problems with double buffering is sometimes, as you have seen, it can compound problems related to slowdown in games. The argument is, maybe you've got these two screens, and the graphics card is looking at one, and you're drawing on the other, and then when you finish drawing this one, you say, okay, do the swap, please. Well, ideally, what you want is that drawing your new image maybe takes like 14 milliseconds or something, and then you say, okay, I'm done now, please swap, next chance you get. And because it takes 16 milliseconds to scan a whole frame, it waits a couple of milliseconds, and then it does the swap, and then you're on to the next frame. But what if it took you longer than 16 milliseconds to draw the frame? Imagine if there was just a lot happening. There were a lot of objects, complex lighting, a bunch of stuff blew up, or which makes rendering time take longer. The problem was that by the time you finished drawing this frame, you've missed the VBlank, and it's already starting to look at the to draw the new frame again, and you haven't had time to do the swap because you didn't finish drawing it. So it's actually going to redraw the old frame again. It keeps the same buffer, and you've kind of missed your chance to swap it, and you won't get another VBlank until another 16 milliseconds has passed. So you end up skipping a frame. Now in a well-balanced system, if things are working fine, like I say, if you can render in 14 milliseconds and your refresh rate is 16 milliseconds, it's not a problem. But what tends to happen is, because you try to make your game as fancy as you can, you always kind of go close to the wire there. You always want to kind of put in as much stuff as you can. And then sometimes it just ends up being a little bit too much stuff, and you fall off this time limit, and then a whole frame gets lost. And the downside of that is that you've got your game and it's chugging along at 60 FPS and it's basically fine, and you enter a new room where it's things are a bit busier than normal, and instead of it just getting a little bit slower, maybe the room it's 10% slower to compute this stuff, instead of the game getting 10% slower, it actually gets, well, 50% slower. Because it completely misses the frame and has to wait for the next one, it goes from being at 60 FPS to 30 FPS. And when it drops as much as that, you can really feel it. The game's quite fluid, and then at a certain point, it's like suddenly a lot slower all of a sudden. That's what's happening. That's because the double buffer has missed the VSync and had to wait for the next one. And consoles are kind of quite notorious for this problem, I find. So that's what happens. You get a little busy section. It takes a little bit too long to draw the frame, and your 60 FPS game becomes a 30 FPS game for a few frames or a few seconds until things eventually kind of return to normal. And it's really annoying because you kind of know in your heart, it's like, it shouldn't be like this. It's like, I was only 4 milliseconds late drawing the frame, and then you have to wait and twiddle your thumbs for 12 milliseconds, during which you're not doing anything because you can't, right? Because you can't touch the front buffer because that's being scanned, the player's looking at it. You can't touch the back buffer because you've just finished drawing it and they haven't seen it yet. So you've got nowhere to go. So it's really annoying that the machine has to end up just like wasting time because it's slightly missed a deadline. It really is literally like missing a bus, It's like you're 1 minute late for the bus, but the bus only comes once every half hour, so you're half an hour late reaching your destination, even though you were only really 1 minute late. So idle waiting is a great annoyance, but that's just the situation that we'd be stuck in. Unless anyone's got a really clever idea.
Triple buffering.
Ah, I see. Yep. The other problem with this is that not only, so if you drop from 60 FPS to 30 FPS, there are two different types of thing that can go wrong. One is, if you're just drawing fewer frames, it means instead of something kind of going, kind of smoothly like this, it starts to go chick, 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 chick. It'll take the same amount of time to get from A to B, but it'll do it more jerkily, right? So that's one thing, jerkiness. It can be worse than that, though. Imagine if your update logic is actually based not on how much time has passed, but on how many frames have been drawn, which it sometimes is in a lot of games. Wrongly, in my opinion, but it does happen. So if you do that, not only does it get choppy, it gets slower as well. It'll take you twice as long for things to get from A to B. So not only do you get bad animation, because the frame rate's not good, you get slowdown, literal slowdown. And you often see the combination of the two. It's why it feels so bad is because you've got slowdown and you've got bad frame rate. It's very annoying. The reason this happens is that sometimes the velocity of objects in games is kind of computed as the distance that they will move per frame as every new frame is calculated. And because when you get into this state where you're idling, so you're not actually updating the logic, it means you're only updating the logic 30 times a second when it should have been 60. Therefore, things will only move half as far per second as they really should have done. So I basically consider this an error, a programming error, because what you should do is you should always measure the amount of time that actually passed, and that way you can compensate for this. But there are some reasons why sometimes a game can't do it that way or chooses not to. I think I'll mention in future lectures why it's not always done the way I think it should be done. But the problem is if you do things per frame rather than per second, you'll get this compounding problem of bad animation and slow speeds. Very annoying.
Doesn't the opposite exist as well? For example, a 30 FPS console game which expects 30 FPS is then ported to
yes.
PC and...
Yep, so the question was, can you get the opposite? And you do. Sometimes you get games that they were hard-coded, assuming they'd be running on a machine that, like you say, ran at 30 FPS or something, and you run it on, so you take like an old PC game or something, and you run it on a new PC, it actually runs too fast, because it's in a loop where it's just drawing as many frames as it can, and kind of thinking that they're all going to take, a 30th of a second. But if you're running on a super fast machine that can do 3 times as much work, the game literally runs 3 times as fast, which is like cool in a way, except that it's completely unplayable because all the the timings and stuff are out with the safe zone of human behaviour. So this used to happen as well. Used to be a problem when old games got re-released. If they hadn't been written the right way, you could release it at the time because there was no machine that could run 5 times faster than the one you had. But you come back to it in a few years, and yes, it doesn't run at the right speed. These are all. I'll be talking about this more in future lectures as well, how you fix all that. But as anticipated, if it turns out that double buffering is not working for you, the solution is triple buffering. Does anyone know the quote, "The family had a lot of buffers"? That's from The Godfather. That's how they explain the use of intermediaries to stop Michael Corleone from getting his hands too dirty. And also it's a bit of a kind of standard quote in computer science that all problems in computer science can be solved by adding another buffer, except for the problem of having too many buffers. So the problem we have with double buffering is that if you miss the bus, you've got to sit and wait for the next one, right? Well, the solution is have another bus, have a spare bus, have a third one that's ready to go just when you need it, and that's basically the trick. So you have your double buffer, and normally you double buffer, but if it turns out you missed the deadline and you're in this position of, I can't change this one because you're looking at it, I can't change this one because you've not seen it yet, you kind of say, I wish I could do something. Well, you can. Get a third piece of paper and start drawing the next frame on your extra spare piece of paper. That way you're not twiddling your thumbs for 12 milliseconds. You can get some work done, and that helps you to catch up. That way you can kind of get that one done, and then eventually the buffer switches from this one to the one that you previously drew. Meanwhile, you're nearly ready with the next frame. So if you do this, you can kind of stop the slowdown from lasting as long. And that's called triple buffering. And it can be quite a good idea. What would happen with triple buffering is it doesn't stop you from having occasional late frames, but it means that when they happen, they don't put you into this horrible zone where you're wasting a lot of your time, not getting anything done. You're running at 30 for a long time. It means you just get a small hitch rather than like a prominent slowdown. So that's quite good. The downside is you need a third buffer, and buffers take up memory. And actually sometimes, depending on your rendering technique, when I say one buffer, there might be many buffers behind the scenes. Sometimes with complex renderers, you're drawing one buffer for the main surface and a different buffer to do like the shadows, and then you combine them together and all this kind of thing. So sometimes the memory costs of creating the third buffer are something you have to worry about, especially on a console. Consoles have got limited memory, so there's always a trade-off. You can say, yeah, we can go to triple buffering, but if we do that, we've got less texture memory. So the textures in your game can't look as nice, and you have to kind of trade it off with the artists as to, well, do you want more textures or do you want the kind of security of triple buffering? You just have to decide. So there's another approach you could take instead of triple buffering. The problem with triple buffering is you're kind of spending this whole extra buffer of memory that you might have other things you'd rather use it for, and you only use the third buffer occasionally, or at least you only need to use it occasionally. The idea is that a lot of the time double buffering is enough. So there's a compromise position called adaptive VSync, where the idea there is you say, yep, normally I'm going to draw and wait for the VSync and then I'm going to flip, except if I was only a little bit late, instead of waiting for the next bus, I'm just going to do an instant switch. So the idea is you were a couple of milliseconds late, you realise you missed the VSync, and you just say, screw it, just change the buffer anyway. Now, the graphics card is rescanning the frame at this point, so when you suddenly switch it kind of underneath it, what will happen? What will you see if you do the switch outside of the VBLANK? A screen tear, right. So we go back to the screen tearing. But you only get that screen tearing for maybe 1 or 2 frames. It's because it's a way of pulling yourself out of this nasty spiral that you're getting into. So some games, that's what they choose to do. They use VSync most of the time, except when they realise that they're getting slow, and they say, I've got a choice here. I can allocate a third buffer, and they've said, no, we don't want to do that. Or, so if you can't do the third buffer, it's like, I'm going to fall down to 30 FPS. Or I could say, no, I'm going to stay at nearly 60 FPS, but you're going to get a little bit of tearing for a while. And I think this is quite common now. You'll see if you move around in a game, you get the tearing, but it doesn't have a frame rate crash. And that's a choice that's been made to do VSync, except when you don't. Yeah. And that's not bad. It's a reasonable compromise, right? Because most of the time everything looks good. It's just that in the situations where it would have been horrendously slow, instead of looking slow, you put up with having a slight visual artifact instead. Another thing I'll mention, we've been talking a lot here about frames per second. FPS is annoying. Of course, it means frames per second and first-person shooter. So those two acronyms collide all the time. But gaming people, they care a lot about FPS. They're always kind of monitoring their FPS rate, sometimes in kind of silly ways, because there's diminishing returns, right? It's like if you've got 120 frames per second, I don't think going up to 240 is really that much better. There's a limit to what people can perceive, so it can be a bit silly. As I say, yes, there's diminishing returns to your perceptual abilities here. So being totally obsessed with high frame rates is not really the right thing. And it's not worth having a frame rate that's higher than the refresh rate of your screen. Another point. However, there is one argument for having very high frame rates, which is that it's not that it looks any better to your eye to have it running at 200 frames a second, but if it was running twice as fast, it's taking half as long to do each frame, and that means that the input latency, which is the time between you making a move on your keyboard and you getting the result on the screen, that gets reduced with high frame rates. So that's one of the reasons that pro gamers love high frame rates, but for them it's a control issue. It's to make sure that when they do something, the effect is seen very quickly. It's not the visual effect of high frame rates for animation, it's the playing effect of having reduced input lag. Nevertheless, you do get some weird things, maybe not so much nowadays, but I remember there was a time when game reviews would sometimes include benchmarks where they would try and trace the average frames per second rate of a game. And this would be seen as like a very relevant fact. But it turns out if you've got you can sometimes have like a fairly high FPS, but periods where it craters to like really low values, and that's worse than just having a slightly lower frame rate that's consistent. So sometimes consistency matters more than having a high average, and they're not the same thing. It's just worth remembering. And sometimes there are trade-offs you make when you're designing a system. There are like sometimes you can come up with optimizations that might help under some circumstances, but they're worse on others. And this is where you have to trade off. You say, well, what do I want here? Do I want like the really busy frames to be fast, or do I want the consistency from one frame to the next to be high? And you make decisions about these things. Also, frames per second is not really a very good metric because it's frames divided by seconds, so it's inverse seconds. It's an inverse time metric. That's not really what you want, because it means that if you talk about I could do something to my game that would make it 5 frames per second faster. That's not really meaningful, because the difference between going from like 25 to 30 is not the same as the difference from going to 95 to 100. Right? So a frame per second is not really a sensible unit. The sensible unit is time. So as a developer, you should think more about seconds per frame, because it's time is the primary variable here. Turns out seconds per frame isn't what you want, because it has to be milliseconds, just based on how long it takes to do things, right? So you'll tend to hear me talking about 16 milliseconds instead of saying 60 frames per second. Because you can meaningfully say, there's something I could do that would shave 2 milliseconds off the time to draw this picture, and that's meaningful, which is not, you can't really say it'll save 3 frames per second, because that would depend on how long it was already taking. Anyway, it's a detail, but I would recommend that you think about how many milliseconds it takes to do things. Right, we have an additional problem nowadays with modern systems. I think that all the stuff I've said to you is still true and is still relevant. Unfortunately, nowadays it's even more complicated than what I've described. Because what I've described is a world where basically the CPU is computing the frame, and it's just the CPU is negotiating with the graphics card to do all the flipping stuff. Actually, what happens nowadays is the CPU is preparing a bunch of instructions that it sends to your GPU, the graphics processing unit, and it has a bunch of buffers that it's got internally where it's managing its tasks. And this can mean that you get problems where, sometimes the game is slow, not because the CPU has been too slow preparing the frame, but it's because the GPU has become overburdened. Or sometimes it's the other way around. The GPU is doing fine, but you've still got crappy frame rates because the CPU is being slowed down by something. So it's just another layer of complexity in the whole mix. So it's buffers all the way down. You got buffer, delays, pipelines, queues. They all make things difficult. So that can kind of become annoying. When you're doing real work, sometimes you have to be aware of this. You have to know whether your game is, we call it either CPU bound or GPU bound, which is you're working out which of those, because the CPU and the GPU are basically running in parallel, and the kind of question is, well, whichever one is taking the longest is the problem. The other one doesn't really matter. But sometimes the CPU is slow, sometimes the GPU is slow. It's annoying. And yes, if you don't get this right, if the CPU and the GPU are kind of imbalanced, that one of them is starved and the other one is flooded, then you get back to having irregular frame rates and stuff, and it can look quite annoying. And that's sort of what that says there. Yeah, okay. Right, so that's the end of the substantive part. So I'll just summarise this, because I know there was a lot here, and some of it's a bit kind of complicated. But here's the distilled version of it. If you had a naive rendering system, you'd you'd potentially get partial images, right, as I showed you right at the start, either in the form of flickering objects or screen tearing. By using VSync, you can kind of hide the partial images because you're only updating them when the Eye of Sauron is asleep. So you fix the partial image problem by relying on the VBLANK. If you then go to the next stage and you have double buffering, that gives you more time to draw the image. So you can be drawing the image, you know, in the background while the other one is being shown, and that's good. And then you just do the swap during the VBLANK. So that helps you stop getting the flickering images. If you have to, you can go the next step beyond, which is to go to triple buffering, and that's a kind of safety net if you get to the point where double buffering is running behind schedule. And as I said at the end, sometimes what you want to be careful about is having consistent frame rates rather than merely having high ones or even merely having a high average. Consistency is what makes it feel good. And as a developer, get used to thinking about how many milliseconds it's taking to draw a frame rather than just thinking about frames per second, which is a kind of user-centric way of thinking. And that is the end of that lecture. Thank God.